Okay, so what was ugly thing? Ugly thing was discontinuity at the boundaries. So, to remove such discontinuity, what should we do is just introduce some constraint. Okay, so let's say this is let's say this is eta 1 and eta 2. Okay, and this is function 1 and this is function 2 and this is function 3. Spline method introduce condition so that f1 eta 1 equal to f2 eta 1, which means these two functions must have the same function value here. f2 eta 2, f2 equal to f3 eta 2. These two functions must have the same function value here. Okay, with these two conditions, with one single condition for each boundary, eta 1 and eta 2, you can enforce the piecewise polynomial function becomes a continuous function like this. Okay, so this function becomes continuous, right? But still, this function is unnatural. For instance, when you look at this point, there's some peak, right? This is non-differentiable part. And actually, this is very unnatural. Okay? Ground truths very rarely have this very sharp peak point. Okay, so this is very unnatural. So to remove such peak point or undifferentiable point, we need to introduce one additional condition such that the first derivative of your function also satisfy this. Basically, we introduce additional constraint to each boundary point so that the first derivative also continues. What about second derivative? Well, in general, the second derivative also usually very smooth. Then we have to add one more constraint. The second derivative also have to be continuous over whole range. What about third derivative? What about fourth derivative? What about fifth derivative? So the spline method is this. Spline is the piecewise polynomial function. So at each range, we define a function f1, f2, f3, f4, f5 for each range with degree d polynomial. So each function have d plus 1 parameters, right? With constraint for each boundaries. This is eta 1, eta 2, eta 3, eta 4. This is called knot. boundary. So we introduce some conditions for each knot, each boundary, so that f I eta I have to equal to f I plus 1 eta I. The second condition, f I first derivative eta I must equal to the first derivative of fi plus 1 eta I. Third condition is fi second derivative up to fi d minus 1's derivative at I have to equal to fi plus 1 d minus 1 derivative. So at each knot we introduce the constraint. Okay, so why not include fi this derivative? Why not? If you include this constraint as well, then which basically means fix equal to fi plus 1x for all h. So which means there's no meaning splitting your input range. Okay, so you don't have this condition, but you have the condition for each knot. Okay, right. And here another important remark is essentially each interval introduce d plus 1 additional parameters because we define degree d polynomial for each interval. So essentially each knot add d plus 1 parameters, d plus 1 degree of freedom. But each knot also introduces the number of constraints, and each constraint kill one single degree of freedom. So overall, each knot introduces d plus 1 additional parameter, so d plus 1 degree of freedom, but each knot introduces d constraint, so which decrease the d degree of freedom. So in total, each knot increase single degree of freedom. Okay, so in total, your spline method has degree of freedom of your spline methods with degree d polynomial is at the first range or first interval you have d plus 1 parameters, so you have d plus 1 degree of freedom, and the first knot increase 1 degree of freedom because d plus 1 additional parameter increase d plus 1 degree of freedom, but d constraint kill d degree of freedom, so in total you just increase single degree of freedom. So each knot increase a single degree of freedom. Okay, so when you have k knots, your total degree of freedom is d plus 1 plus k. Okay, so this is total degree of freedom of your spline method. And in general, many people love to use cubic spline. Cubic spline is the most popular selection for your spline method, and cubic spline has 3 plus 1 plus k degree of freedom. Okay,